The moment of inertia is an important concept when we're dealing with rotational motion. So our moment of inertia, we can define as the sum of all of the individual moments of inertia of every single particle within a system. Now, the moment of inertia of an individual particle is the mass of that particle times the distance that particle is away from its pivot point, and that distance will be squared. Now, this is what this equation is saying. The moment of inertia, represented with a capital I, is defined as the sum of all of those individual moments of inertia, where it's the mass of each individual particle times the distance of each individual particle squared, and that distance is the distance away from its pivot point. So really what this means, though, is the moment of inertia depends on both the mass of our object and the arrangement of the particles that constitute that object. In this equation, the I is each individual particle or the ith particle within that system. Now, this is going to be a very important concept to focus on. The moment of inertia, as well as how it relates to inertia. To do this, we're going to look at Newton's second law of motion. In linear motion, the way that equation is written is the sum of all forces acting on our system is equal to the mass of our system times the linear acceleration of our system. The rotational motion version of Newton's second law is the sum of all of the torques acting on our system is equal to the moment of inertia times the angular acceleration of our system. Now, these two equations both are different ways of writing Newton's second law of motion. They're currently written in the same format to be able to relate each individual term. Our torque is going to be the relationship between the force and the distance away from a pivot point. So the torque would be the rotational motion analog of our force. Our angular acceleration is the rotational motion analog of our linear acceleration. And our moment of inertia is the rotational motion analog of our mass. Now, when we're focusing on the mass in linear motion, what we really are focusing on is it as a measure of the tendency of an object to resist changes in its linear motion. This is why a lot of times we refer to the mass in this equation as our inertial mass. Some people even refer to that just as the inertia of our system. The mass of our system, or the inertia of the system, is that object's or that system's resistance to changes in its linear motion. That should be contrasted against the moment of inertia, or the rotational inertia of our system. The moment of inertia of an object or the system is a measure of the resistance of that object or system to changes in its rotational motion. So m, that inertial mass, is the resistance to changes in linear motion, and this capital I, the moment of inertia, or the rotational inertia, is the resistance to changes in rotational motion. Now, the reason why we typically see Newton's second law written in its linear format is because mass is an intrinsic property of an object, whereas the moment of inertia depends on both the amount of mass the system has as well as that physical arrangement of the mass. Now, there are ways to actually quantify the moment of inertia for different objects. Because while this definition is very useful for having a conceptual understanding that a larger moment of inertia would be corresponded with objects having their mass distributed at greater distances, it's not super useful if we actually want to use the moment of inertia in this equation. Right here are some common moments of inertia. Some very common shapes are cylinders or discs and hoops, because these are basically wheels, things that roll. We have solid and thin or hollow spheres, like a ball that rolls. These are going to be some really common shapes that we see when we are analyzing rotational motion and trying to determine moments of inertia for these shapes. Now, quite often, we'll be using these equations so often that you may end up memorizing them. However, in most situations, you do not need to memorize the common moments of inertia. On assessments, the equation will often be given to you. On homework assignments, you'll often be given the equation, or you'll be have access to the internet where you can Google the equation for a moment of inertia. You might have a printout similar to this. It may not be overly beneficial to memorize these equations, but rather just understand what each equation means. This is our definition of the moment of inertia. When we're focusing on a system, such as any of these, the mass of that system presumably is going to remain constant. So what we really need to be focusing on is that distribution of the mass within the system. The further away from the axis of rotation, or that pivot point that the mass is, would have a greater R value, which means we would have a greater moment of inertia. For these 8 different shapes that we have here, the hoop that is rotating about its symmetry axis is the one that has all of its mass at a distance of 1 radius away from this axis of rotation. That is why for this moment of inertia, the coefficient is 1. That is the greatest coefficient that we're seeing in front of any of these mr squared or ml squared equations. That's because all of its mass is at its greatest distance. Whereas objects that are solid, like this solid cylinder or disc that is also rotating about its symmetry axis, in much the same way this hoop is. It has some mass at a distance of 1 r away, but it also has some mass at a distance of 1/2 r away, 1/4 r away, 1/16 r away. It has a distribution of mass throughout the entire object, which is why its moment of inertia is lower than the moment of inertia for the hoop about its symmetry axis. We can focus on that conceptual understanding of the moment of inertia for any of these shapes, based on how far away each particle is away from its pivot point.